welcome to the second lesson of the first unit. And in this lesson, we'll be discussing how to analytically evaluate limits. Specifically, we'll be looking at using algebraic properties of limits and using algebraic manipulation to determine limits. In the previous lesson, you looked at evaluating limits numerically and graphically. You also saw that a limit may not exist at certain values of x, where the limit from the left is not the same as the limit from the right. Today we'll be discussing that further, or when the limit approaches infinity. Additionally, the limit of a function does not depend on the value of the function. A limit can exist, but the value of a function may not. In today's lesson, we're going to take that a step further and look to see that some functions' limits can just be evaluated at the value of the function. So we'll start really simple with some basic limits. Okay. The limit of a constant value, for instance, the limit of b as x approaches some number along that line, is just b. The limit of a linear function like x as x approaches c is just the value c. You're plugging in the value of c for x. And with a power function like x to the power of n, x squared, x cubed, that type of thing, again, the limit of that function as x approaches c is just the value of the function. I'll let you pause the video and take note of some other properties of limits. And just some quick notes. These properties are going to come up a lot when we talk about derivatives, when we talk about integrals. They're going to have a lot of the same types of properties. We can scale limits. We can add or subtract limits. We can multiply limits. We can divide limits, provided that the denominator isn't 0, of course. And we can raise limits to a power. And doing so has a very intuitive effect. Okay. So for our first example, we're going to be talking about direct substitution. We want to find the limit of this function, 4x squared plus 3. The limit as x approaches 2. So the very first thing that we should try is, can we just plug the number in? So, using property 2 from the theorem 1.2, you can see that polynomial can be broken into two smaller pieces. We can add those limits together. We can factor out the 4 from the first part. And then we can just directly substitute 2 into x squared. Simplifying, we get that the limit is equal to 19. What other types of functions can you think of that could be evaluated by direct substitution? Pause and think for a moment. So some other basic limits of some function families, I've linked a video below. So all of the function families that we talked about, or that you talked about in Algebra 2 and pre-calculus, all of those functions that have, and I'm going to use a word that we are going to talk about later in this lesson, that are continuous or have known domains, all of those functions can be, limits can be evaluated for by usually just direct substitution. Now let's take a look at a rational function. Rational functions are oftentimes a point where limits become sometimes a little bit more difficult. So we'll try our direct substitution. We look at the limit of the numerator, the limit of the denominator, and they actually both end up being 0. And as you know, we can't divide by 0. So our direct substitution failed in this instance. But that numerator does factor. And we can cancel a factor in the numerator with the denominator and see that this function is equivalent to the line x minus 2, but there's a hole at x equals -3. However, the limit of this function evaluates to -5. So in quick summary, a lot of limits can be evaluated through direct substitution. Direct substitution should be the very first thing that you try to evaluate a limit. If direct substitution fails or you get some weird result, you may need to try to simplify the function or make the function look different in some way. I've linked a cheat sheet that shows a flowchart of the way you should think about evaluating a limit. Before you go, there are 3 special limits that I wanted to introduce you to, and you'll have some time to practice with these during your practice routine. So some three special limits. The first one is that the limit as x approaches 0 of sine x over x is equal to 1. You can verify this with a graph. You can verify this with a table. Okay. The next is the limit as x approaches 0 of 1 minus cosine x over x is equal to 1. Again, this can be verified using a table or looking at the graph. And the last one is really cool, and one that you're going to be exploring a lot more in detail with some groups. And that's the limit as x approaches 0 of 1 plus x to the power of 1 over x. And that's actually equal to a special number e. And so you're going to have an opportunity to explore that function in a group work activity later today. Thanks for watching.